Welcome back everyone. In the previous session, we provided an introduction to the k-means clustering method, how it works, and we went through and tried to identify the centroids and placing it onto the actual clusters, the individual clusters itself. Now, the one thing that we learned is that the way that the actual centroids is placed with each clusters is based on the method called within cluster sums of squares criterion. Basically, with that, it tried to minimize this value here. So let me just highlight this. This is what we're going to work with in this session now that we're going to talk about the elbow method. Now, the challenge that we have had in the past and still us having this challenge is that because we're working with unsupervised machine learning method, we don't actually have an answer to go with it. So as a result, we have to resort to a slightly different method to evaluate the performance of this model. So typically what we do when it comes to clustering is that we use what is called an intrinsic matrix, which is another word for the within cluster sums of square errors. Basically to compare the performance of different k-means clustering. Now the beauty of this is that scikit-learn library has provided the inertia attributes to go with it. So we don't actually have to calculate all of these ourselves. You just need to actually extract it directly from scikit-learn and you'll be able to actually resolve all of that. So what have we done here? Let me just show you. This is a continuation of what we did earlier. So if you look at this, the so-called inertia, and notice that there is a value to go with it. This is to go along with what we actually said before. I believe we set a cluster of 9 and the sums of squares of error is this. Okay, now let's run through how the elbow method actually works. So we're just going to use SSE. Okay, sums of squares of errors is equal to basically a list. Basically, this is right now is 0. So we're going to use a for loop for k in the range from 1 to 15. Well, we have no idea how many clusters to try, so we're just going to try from 1 cluster to all the way to 15. So we're just going to rotate through them all. So now we're going to instantiate the k-means itself using k-means. And number of clusters is based on k, which is actually provided based on this here, this k here. And then for each one, we're just going to fit immediately to the actual x value itself. Now, with the sums of square of error, we're just going to append to it. And we're going to append a couple of things. K, because we want to know this sums of squares of error is to do with which cluster. Is it 1 cluster, 5 clusters? So we store that as well. So k means an inertia. Okay, and finally we just need to run that. Okay, so that now that we've run that, so we just need to plot this. PLT plot. We're gonna plot it as a data frame. We're gonna use SSE and 0. This is the column 1, and again I'm gonna use data frame, sums of error, and then we column 1. So what we are doing here is that we're plotting the x-axis. This is feed in as the x-axis, and this is fed in as the y-axis. So let's plot that out and see what happened. Okay, right. Welcome back. I changed the actual naming a little bit. It seems like there's some sort of conflict with the SSE and also with the variable name that we use, which is SSE. So I changed it to SSE underscore, and this is what we actually get. Again, we rotate through. So let me just walk through this again. We're gonna change this to 15. And we're storing everything. We basically instantiate and fit at the same time, and then we are appending all of the value to the SSE underscore. So let's just plot this, and what you can see here is by the time you get to number 8, it's already flattened out substantially. So we don't need to go that far. So let's run with 8, and okay. Now this is the part whereby, okay, it's how you actually make use of this elbow method is like this. If you understand the basic idea of elbow, that's basically how this works. Typically, if you're looking at and thinking of the elbow, you probably will think 4 it's actually okay, 5 is okay, and 3 is okay as well. There's no straightforward answer to this. Any of these works just fine. Okay, so typically you may want to choose 3, but notice that at 3 the sums of squares error is quite high. At 5 it actually starts to plateau off, and from here onwards you're not really getting much in the way of value. From 5 or 6 onwards, I should really say, you're not really getting much in the way of reduction of the within clusters sums of squares of error. And that's really the basic idea of the what you would call this elbow method, is that you are looking for this kink, this part here. Okay, and in our case, this can be considered one, this can be considered one, and the 5 one is probably the least of the lot, but nevertheless, you can actually choose 3, 4, 5. It would not be wrong, primarily because we are looking at unsupervised methods, so any of these 3 points here is just fine. So that's pretty much what I want to cover when it comes to the elbow method. When we return, I want to actually cover another way of identifying the ideal clusters, and that topic is called silhouette. So we're going to leave that here, and thank you for watching. I look forward to seeing you in the next lesson.